Okay, so today we want to look at the lecture on cadre sense multiple access with collision detection, and also cadre sense multiple access with collision avoidance in data communication and networking. So now let's look at first of all what cadre sense multiple access is. So cadre sense multiple access, basically, the idea behind it is to listen before you transmit. Because this is a concept that is in medium access control, where you've got shared media, then you have to use that shared media without causing any collision and interference to other computer that wants to use the same media. So the MAC, which is the medium access control, has these principles that you want to discuss today. And these are cadre sense multiple access. So with this principle, you must remember that you need to listen before you transmit. In this way, it makes the channel that is shared not to be overwhelmed and then cause collision. In other words, we are saying before you use the shared media, we have to understand if at all the shared media is idle or it is still busy. So the cadre sense multiple access, first of all, you need to sense the channel that you're using, if at all it is idle or not. If it is idle, that's when you need to transmit the frame that you want to put there. And if that shared media that you're going to use to put data on, if it is busy, you sense that it is busy, then you defer the transmission. You transmit later on, not at that particular moment. So basically, these two ideas under cadre sense multiple access normally helps the computers that are competing to use the same media for transmitting data to avoid interfering or colliding with each other. So the idea is first you listen before you transmit, which means sense if the channel is idle, then you transmit the data. Otherwise, if the channel is busy, then you defer the transmission, you send at a later stage. So this arrangement is quite common to human setup, where we don't want to interrupt others as they speak. All right. You find that when you are talking, you're trying to convey something to someone, which is very important. Then someone is also talking. Of course, you say don't interrupt, because what you want to do is you want to make that message reach the heart. Otherwise, if someone is talking as you're also talking, you find that there will be that collision in terms of the messages that you're trying to convey to each other. So that's what cadre sense multiple access is quite similar to the way human beings would like others not to interrupt them as they try to communicate. All right. So now, cadre sense multiple access collisions, right? So collisions can still occur regardless of this principle. So the propagation delay means two nodes may not hear each other, it's transmission. So you find that as you try to communicate, and then the nodes are actually competing for the use of the media, and if it happens that they put the data on that media at the same time, there will be collision, right? And the delay that is there, the one that you're calling propagation delay, will mean that the two nodes will not able to hear each other when they transmit. So you find that when collision occurs, the entire packet transmission is wasted. That's a problem. Imagine you're trying to send a message, okay, message X to computer B, and then computer B also want to send message Y to computer C, and then they're going to use the same media to put that message on. If it happens that these messages collide, it is as good as doing nothing. That's a danger, that's a disadvantage of collision, because it cancels the entire messages that has been put on that media. So this is the more reason why we need to avoid collision at all costs, because it wastes time and also it wastes the computer resources. So one thing that we need to notice, the law of distance and propagation delay in determining collision is a probability. It's not something that is exact to say This is how long we're going to wait when the collision occurs. It's a probability. You take a random number for waiting. It can be higher number or lower number. The fact is, it is not a fixed number when you're told to wait. It's more like, for example, you want to enter a classroom, and then it is occupied by another class. Of course, when you knock, okay, it might be that you might be responding as soon as possible to, or otherwise it might take more time for someone to respond to you. And if it happens that you try to open the door, you crash the class, you're told to wait outside. Again, it's not something that is known that I wait for 2 minutes or 3, it is by chance. So it's the same thing that happens when the computers collide. They are given the random number, which is not even known. Okay, it can be high number or it can be low number. So all in all, when there's a collision, there is too much delay, and this delay is not something that is known. It can even be more than that, right? So collision in a shared media is something that should be avoided at all costs. It makes the computer lose time, lose the resources, and makes the computers involved lose the entire messages which they need to regenerate from scratch when they want to send the data together. So basically, we try by all means to avoid collision as we try to use the shared media in networking. Right. Now let's look at sense multiplexes now with collision detection. With collision detection. Basically, this is what will solve the issues that we have discussed earlier on. If collision occurs, we have seen those problems that arises when there is collision. So now with this principle, with collision detection, it is going to help the computers not to waste resources such as time and processor time and also the memory resources when there is collision. So how does it work? So the carrier sensing or deferral, as in carrier sense multiplexes, how does it work? So collisions are detected within a short time with this principle. And colliding transmission is aborted, reducing the channel wastage. So in other words, you're saying with collision access, multiple access, right? I mean, collision sense, multiple access. The thing is you detect the collision before they occur so that you avoid wasting the channel's resources. So how does it work? Let's look at the collision detection. So it is easy in wide lines. Basically, the carrier sense multiplexes with collision detection works well in guided media or the wide lines, wide local area networks, because it is easy to detect something tangible, detect something on the tangible media, right? Or the guided media. So measuring signal strength and compare transmitted and received signals in the wide media is very, very easy. This is the more reason why collision detection is suitable for wide local area network. But it is difficult in wireless to use this technique because you cannot actually detect or measure the signal strength and also the received signal in intangible media. Right? So what you're saying is the collision detection is going to work very well, pretty well in the wide local area network. Okay, so we are going to apply the principles that are there in human setup if you want to be polite in the conversation. For example, if people are talking, okay, how would you come in? You just interrupt the conversation? Of course, you excuse yourself, excuse me, can I say something? If they allow you to do that, that's when you can talk. So you're going to apply the same principle. So collision detection applies the same principle of being polite as you are trying to communicate with people that are already busy. So the principles are basically the same. These are adopted principles from the human setup. So even here, with the collision detection, we are going to be applying this concept of being polite. Right? So let's look at this diagram which shows collision detection. Okay, so as you can see from the diagram this side, you can see collision detect and abort time. So once you detect a collision, you abort the time and waste the message that has been put in the media, right? So now, it is this arrangement which we'll try to solve. The time of detection, when you detect, do not engage. Because once you engage, you waste time and resources. So how does this work? Okay, now let's look at this principle, the multiple axis, as you can see from it. Okay, so collision, if two or more nodes transmit at the same time, you find that there is collision as area under 2. So kind of sense multiple access makes sense. Get all the bandwidth if you are the only one transmitting, so that you acquire all the rights of the media, right? And you lock the media, so that whoever comes will not find the media free. In this way, this will not cause collision if another computer senses the transmission and the transmission is locked. Okay, so now this becomes easy with collision detection, but in the case of wireless media, where, as you can see from this example B, where computer A and computer C cannot see each other. Okay, and there's nothing tangible to use to detect. No. With wide media, it becomes easy because the computers will go to the shared media, sense it, find out if at all the media is free or it's not free. In that way, they can defer their communication or transmission, or if it is free, they can quickly put their data there and transmit data. But in the case where there is the problem of hidden terminal, we call it hidden terminal problem, where computers cannot see each other and there's nothing they can use to sense. It's intangible. So this becomes a problem. So how do you sort out this arrangement of hidden computer problem? And this is now, it brings to second principle we're calling the sense multiple access with collision avoidance. Okay, another medium access control protocol. So now, with WAD, we have established the fact that you do sense multiple access with collision detection, where it is very easy because you go to the shared media and find out if a tool is free or not. But where there is no tangible media, guided media, how do you avoid collision? In this case, you endeavor to avoid as opposed to detecting it. So with sense multiple access with collision avoidance, what you need to do is before you transmit anything, you have to send a control bit. All right? A control bit is more like a request bit, request for transmission. We are trying to find out if at all you can transmit. So you send a control bit to the computer that you cannot see, right? And then the reply will come, indicating whether this computer is free or not. So you start by sending a control bit, a message that is a form of request to transmit. Then, if the reply, the acknowledgement comes to say the computer is free, then you will request to establish a connection which you're going to use to send data. This is where the three-way handshake applies. You request for communication, the acknowledgement comes back, indicate if it is free or busy. If it is free, then you establish the connection, then you put the data there. So basically on the sender side, what happens is if sense channel idle, then what do? Then transmit entire frame, right? Which you sense by sending a control bit. And then you wait for acknowledgement to come, which will contain two messages. Either the channel is busy or you need to back off, right? The channel is free, you need to send. So this is how the acknowledgement comes. So the sender will be waiting for this acknowledgement. Remember I said, this is similar to human setup. If you're being polite, you want to communicate to people and then they're busy. They are trying to talk to other people. And then the message wants to give them is important. You just chip in. Of course, you excuse yourself. Then you ask, can I go ahead with what I want to say? Of course, if they have got enough time, they've got room for you, they can say, no, please go ahead. Then you can actually communicate and put that message across. But otherwise, if they say, no, we are still talking, you're busy, come back some other time, then you back off. Now, that's where the problem is. When you back off, it's not that you wait for some specific time, which is standard. That number is random. So it can be higher number or lower number. So the fact is, when you back off, you come back depending on the random number that will be given. Then on the receiver side, if you receive the okay, which is under the acknowledgement, then you need to actually accept, okay, demand that the sender establish the connection and able to send or receive the data. So the MAC protocols, that is the carrier sense multiple access with collision detection and carrier sense multiple access with the collision avoidance, they all work more like the way as we operate when we want to be polite. When we're in the group of, okay, when in the midst of other people, we are trying to communicate to different people and want to be getting chances to have to get hold of each other's attention so that you can communicate. So the best thing to do is to be polite for you to be given the right answer. Otherwise, you'll be brushed off and there's nothing that you can do. So being polite is what the MAC protocol principles are all about. Okay. So now collision avoidance mechanism. Look at this problem. Two nodes hidden from each other transmit complete frames to base station. The base station basically is a computer or it can be a phone. So two nodes hidden from each other will transmit complete frame to a base station. And if the base station is busy, you waste it, right? And then wasted bandwidth for a long duration. Okay, you waste the bandwidth for a long duration. So what are the solutions to the above problems? Small reservation packets. You will send small reservation packets. Like I mentioned earlier on, you can start with a control bit, a small message for request before you put the entire data on the bandwidth. Nodes track reservation intervals with internal network allocation vector, right? So you find that you will, okay, track and reserve, okay, for the data that is going to be sent from the sender to the receiver. You will track and you specify the intervals, which means, okay, within that specified time frame, if nothing is happening, you close the channel, right? You don't wait a bit very long, anytime for any time, no? You have to be given a specific time of wait. If nothing happens in that period or time frame, close the channel, or you're going to waste the bandwidth. Right. It's not like, for example, someone comes to you and say, I want to talk to you. Right? They expect that if you say, okay, go ahead, quickly, someone start talking. Right? Now, you find that other people are quite irritating. They will take time. They will say something again. For them to say the next sentence, it takes time. You find that you even a system to finish statements. Oh, this, that is not very good. Because even us, okay, we are very busy people. We don't want to waste our time. So we want to get the message quickly. So in other ways, automatically we give someone time intervals. Otherwise, if that person keep on talking in that manner, the brain completely shuts. So in that way, to avoid wasting bandwidth for long durations, you give reservation intervals when you can actually accept the data or reject it or even drop it. Okay. Now let's look at collision avoidance, okay, in terms of request to send and clear to send. We call them RTS, which is request to send, and CTS, clear to send exchange. If you check on this diagram here, it is clearing, as you can see, clear is C9. The source, the destination. Okay, so what happened? So the sender transmits short, okay, message clear to send packet indicating the duration of our transmission, which have been always been referred to as a control bit. Okay. Then the receiver replies with a short message clear to send. In this way, you avoid wasting resources, because if you put the whole message, boom, okay, and then they'll find that the computer's busy, it's wasted. What have you done? You've wasted the computer time. You have to regenerate the same message again. That's costs time also, and other resources that you waste. So before you put the free data, you must send these short messages, okay, between the sender and the receiver. As you can see, the source will send the RTS, the request to send, and then the receiver, the destination will also send the CTS, the clear to send. That's when the data now is transmitted, right? So the ET node will not transmit for specified duration, okay? That is if at all there's a problem of collision, or maybe there's a problem of the acknowledgement which comes is not clear into send, right? So which means the hidden computer will not transmit for specified what? Duration. So before this big chunk of data is sent, do the RTS, do the CTS, and send. Then you acknowledge that the transmission was successful. I think this is what we do, okay, if you are trying to be polite. Even though sometimes we, because of the way life is, we try to abrogate the principles of being polite in conversation. We find that people are talking, talk, we don't care. But normally, we excuse yourself. It's short message. Someone says, okay, go ahead, please, short message. Then you put the message. You don't just talk. So this, okay, adoption of our humans who are polite when they're talking has been adopted in computer networking, more especially when the computers involved are too many and they're trying to exchange the messages. Okay. So it's a very simple protocol. There are simple MAC address protocols, which helps us to understand how computers avoid the collision and how they detect what? Collision. So the RTS and the CTS, okay? Collision is less likely of shorter duration, which is very what? Very true. So if the durations are shorter, you likely have this what? Collisions. That's what this means. You find that if you send these shorter messages, probably collisions, even if they might occur, they'll be shorter durations. And end result are similar to when you detect a collision. The period is actually shorter if you detect a collision as opposed to getting into a collision. So that's the purpose of having the RTS and CTS, is to, in case something, in case you collide, in case the RTS and the CTS collides, these short messages, they've got shorter duration to sort out the problem, as opposed to the bigger what? Message, which is similar to the collision detection. If you detect a collision earlier on, it is the correction time is shorter than when the collision occurs, it's quite long. Okay, so you find that the IEEE, which is Institute of Electronics Engineering, okay, allows sense multiple access to be divided into two. That is the collision detection for wide networks and collision avoidance for wireless computing network, or rather communication networks. Right. So as we are actually talking, we have established the fact that collision wastes resources. That is time, okay, and the memory, right, of the computer. And to solve these problems of collisions, the medium access control has come up with two protocols, okay? Has come up with two protocols, of which one works well in wired and other works well in wireless. So at this point, we have looked at how both of them solve the problems which are there in these categories of networks, right? So now we can see again that as we look at this, You can see that this is adopted from our humans. Okay, when they endeavor to be polite, how they communicate is how the computers adopt that gesture, which is what biases multiple access. Right. So what's the summary? So the summary of what you've discussed, which is the medium access control protocols, we have looked at this question: what do you do with the shared media? What do you do with the shared media? Remember the previous lecture, or this is the continuation of the previous lecture. With the shared media, we partition it, we divide it into time, frequency, and fault. Hence, we had those divisions we discussed last time: the time division multiplexing, fault division multiplexing, and frequency division multiplexing. But today, we have looked at the shared media in terms of carrier sense multiple access, which is used in Ethernet, to solve the problems of collisions, because a shared media is highly, the chances of collisions are very high. So I've looked at also how to avoid the collision in such instances. All right. So following the lessons we had on the shared media regarding how to make use of the same media, we looked at how to use the media, source. Now today we have looked at that same media can be a problem in terms of collision, and we have looked at how we can avoid the same collision which can occur in the media. So this is a follow-up of the previous lecture which I sent regarding the multiplexing and spreading. Okay. So I want you to go through this lecture to complement the previous lecture that we looked at. For now, this is how far I can go in terms of medium access control. But again, I would like to look at something before I wind up. I'd like to look at something before I wind up. Let me look at the OSI model. The OSI model, which basically stands for International Standard Organization. This model is the one which shows how messages should be transmitted, in what form, from what stage to what stage, up to the time that you get the data from the sender. So the message from the source to the destination goes through certain procedures before you receive it this side. More like a recipe for food. Before you receive the food on the table, that food has undergone different procedures. Maybe cleaning it, cutting it, cooking it, all those things until you see it on the table as food. So now, when you receive a message from the sender, you receive it on your terminal or base station, that message has to go through certain procedures before you receive it. So that is the purpose of the OSI model, is to help us understand the procedures and the stages the message go through before you receive it. So this technique, as you can see, it was actually revised in 1995. And then it was called the OSI, the ISO OSI, an addition from the International Standard Organization. Now it was added open system interconnection. So it has been there for some time, even though, as we discussed later on in another lecture, there is a new model that we use, the TCP/IP model. But for now, I would like us to look at this model first. So this model has 7 layers, as you can see from the diagram here. It has 7 layers, of which the first one is physical layer. There's data link layer. There's also network layer, transport layer, session layer, presentation layer, and finally, layer 7, the application layer. Okay, so now let's look at these layers one by one. So let us begin with the physical layer. So the physical layer, as the name suggests, it is responsible for the type of media that will be used when communicate. So the physical layer coordinates the function required to guide a bit stream over a physical medium. So it's the one that tells whether the message will be sent using, right, using the wired media or the guided media, or it will be sent using unguided media. That's the purpose of what? Of the physical layer. Okay? So specify if it is a physical layer, to specify the cables you're going to use, and so on and so forth. Okay. So then, I would like to quickly look at the data link layer, this one, right? Because my main focus is to help you understand each of these layers and what they do. So now, the data link layer is responsible for attaching information that will be useful for the message to move from one computer to the other computer. Basically, the data link is the one that is responsible for the header information in the frame. By this time, we must be able to understand that when the message is moving from one computer to the other computer, it is called a frame. The frame is a addressed packet. In that, it has the header and the trailer. Now, the header is the one that has information of the source address and the destination address, where it is coming from and where it is going to. So now, the layer which is responsible for attaching the header to the frame is the data link layer. Okay. So, let's look at this other layer 3 now. Okay. Layer 3, which is a network layer, is responsible for the trailer. Okay, the trailer in the frame is basically meant for error corrections and error detection in case the message, okay, suffers distraction along the way. Okay, how will the computer on the other side be able to know that this message has suffered some distraction? So that's where now the network layer comes in to provide mechanisms that to ensure that the message sent is not altered or changed, right? So to put mechanisms which we'll look at later on, such as the block parity method, the parity check method, the checksum, and the CRC, cyclic redundance check. Okay, these are the methods that helps the message, okay, to arrive intact. And if something went wrong, then the receiving computer will be able to tell that something went wrong. Okay, so after layer 3, it means now the packet has become a frame, it is traced. It has the header from the data link, and it has the trailer from the network layer. So now the transport layer now will do what? It's not, for example, now you have managed to buy, okay, for the letter, you have managed to buy an envelope, and you have managed to stamp it, you have put both addresses, where it is coming from and where it is going to. So what do you think the post office will do? Will carry that letter now and move it, because now they know where the message is going to. So that's the purpose of transport layer. Since a frame is already there, it has the header and the trailer, then the purpose of this layer is to deliver the message. So the transport layer is responsible for process-to-process delivery of the entire message, okay, to the application program. So that's the purpose of the transport layer. So again, if you remember from the physical layer, if it was specified that this, okay, this type of communication is going to use guided media. When I say guided media, I'm referring to the wired media. If I say guided media, I'm referring to wireless media. So remember those points, I'm going to use them from time to time. So now, if the physical layer specify that this is a guided media, a wired media, you find that the transport layer is going to employ the TCP protocol, the transmission control protocol, which is good for guided media. Otherwise, if right? The media is unguided, wireless. Then the transport layer is going to employ the UDP, which is the user data protocol, which is good for wireless transmission. So that's what basically the transport layer is all about, is to carry now the message to the other terminal. What about session layer? What does it do? This, okay, service provided by the first three layers, that is the physical data link and network, are not sufficient for some process which we have established already. So the session layer is a network dialog controller. What does it mean? It establishes and maintains and synchronizes the interaction among its communication systems. It is specific responsible for transmission layer, which includes the dialog control. So this is the one, okay, which now specifies for how long the message, okay, the communication will take place. For how long? That's the purpose of what? The session. Okay. So again, how long, in case there's something wrong, how long should you wait for the response? It's a session layer. So when you transmit the data, there will be a session to say, for example, within 3 seconds, the data has to be received in full. Thereafter, otherwise, if it's not that the case, then there's something wrong. They transmit again. When you transmit, you don't just wait a bit right long. You have to specify for how long should I wait for a transmission. So this layer is responsible for such arrangements. All right. Coming to a presentation layer. The presentation layer, as the name suggests, is concerned with the syntax and the semantics of the information exchange. We all know very well that on the internet, we use different computers with different physical properties and coding systems, right? So it is this layer which is responsible for interpretation of such discrepancies in terms of physical properties, the coding systems, okay, and the like. So if the message is coming from a different, okay, system that has different coding system, then this layer will understand where the message is going to, and it will be able to interpret or translate that code into the code that will be accepted, okay, to the destination and vice versa. Right, so that includes interpretations, which are the translations, the encryption techniques, okay, decryption is also done at the presentation. If the data was compressed, decompression and compression, all this is done at the presentation layer. So if the message is now decompressed, then it can be read at the application layer. So as you can see, at application layer now, it's the point where now the user is involved. Now that's a point where now we get your phone, we get your laptop, and we're able to read the message. Oh, the message has come. Forgetting that it went through all these processes. So at the point of you receiving the message, you must remember that the computer has gone through all these stages that we are talking about. So this is where we find applications such as emails, WhatsApp, Twitters, and all these internet-based what? Applications, as you can see. So from this, okay, lecture that I've talked about, okay, the OSI model, we've got now an understanding. So when you send a message, the message goes through 7 layers before it is received that side. And when someone sends a message, you receive it here, understand those layers that we have discussed. Okay. Now, as I mentioned, this model was modified in 1995, quite a long time. So as we speak, there are new protocols that have come, okay, in internet, right? So because of that, there is a need for us to discuss the new protocol suite, which we are calling the TCP/IP protocol suite. So basically, this protocol suite, the TCP/IP, which is Transmission Control Protocol, Internet Protocol, has just modified the OSI. Okay, so you're saying the TCP/IP protocol suite was developed prior to OSI, right? Therefore, the layers in the TCP/IP suite do not exactly match with those in the OSI model. So the original TCP/IP protocol suite was defined as having 4 layers, okay, which is host to network, internet, transport, and application. However, when the TCP/IP is compared to OSI, you can say that the host to network layer is equivalent to the combination of physical and data. And the internet layer is equivalent to network layer and application layer. Roughly done with the job of the session presentation, and application layer with the transport layer TCP taking care of the duties. So what does this mean? Yeah, what does this mean? Let's not get confused. Let's get that. So what you are seeing here, what you are seeing this side is the OSI protocol with the 7 layers. All right. Now what you are seeing this side is the new TCP/IP protocol suite. So you can see the host to network, right, is a combination of these 2 layers. The data link and the physical link layer, they form the host to network, right? Then the network is basically the one that has become the internet layer. The transport layer, okay, is the same as transport, has never changed. But the presentation and the session have been added, combined into simply part of what? Application layer. All right. So you find that 1, 2 are embedded in the application. So application will sort out the session and presentation according to this diagram. So if you are to understand what the TCP/IP model, you compare the 2 diagrams. And if you are taught to define what these layers in the TCP/IP model are, if you have this diagram here, it becomes easy. Because it's a definition of these 2, what makes this. The definition of this is what makes this layer, internet layer. Transport layer has never changed. Then the definition of these 2, including the application layers, what makes what we call application layer in this regard. So basically, after discussing the OSI model, it becomes easy for you to move to the TCP/IP model. I think for today, this is enough. Okay, for today's lecture. Next time, I'm going to discuss something on signal. Okay, of course, I'm going to do some bit of calculations in the network signals, and the lecture to follow also contain the network security measures. Another lecture which is going to involve a bit of computation. So please, these 2 lectures which I'm going to look at, I encourage you to have also pen and the paper and the possible calculator as we discuss it. All right, so for today, this is how far it can go. Please go through this video. I'm going to send it to you so that you can revise several times so these principles can be part of you. All right, thanks very much.